In our discussion of probability, we've been working with compound events. Recall that this is events with more than one outcome, like rolling an odd number. The event would be 1, 3, or 5. Compound events can come in two forms. We've seen the or compound events with the mutually exclusive events. We could roll a 1 or a 3 or a 5. When we work with compound events using OR, we saw in the previous lesson that we add probabilities of outcomes. So for example, rolling an odd number, rolling a 1 or a 3 or a 5, the probability of rolling a 1 is 1/6. The probability of rolling a 3 is 1/6. And the probability of rolling a 5 is 1/6. So we can add these together and we get the probability of rolling an odd number, which is 1/2. In this lesson, we're going to talk about compound statements with the word and. So take the example for rolling a die. What's the probability we roll a number greater than 3 and it's odd? Considering this example now, recall the outcomes for the sample space for a single die. 1, 2, 3, 4, 5, 6. Greater than 3 would be the numbers 4, 5, and 6. Odd would be the numbers 1, 3, and 5, which in the sample space satisfies both greater than 3 and odd. 5 does. So we're really looking at the probability we roll a 5, which would be 1/6. Let's talk definitions. If you haven't already, pause the video, go to your book, see if you can write down the definitions of independent events. Events are independent if the fact that one event occurs does not change the probability of the other one occurring. Dependent events, the definition would be opposite of independent. Dependent events would be when the occurrence of one event affects the other in such a way that the probability is changed. Mutually exclusive and independent may sound similar in our English language, but they are quite different. For mutually exclusive events, when one event occurs, its mutually exclusive event cannot occur. It is impossible for two mutually exclusive events to happen at the same time. Because they are mutually exclusive, they have nothing in common. For independent events, one event occurring does not prevent the other from occurring, but it may change the probability that it occurs. It may change the probability of it occurring. If the probability is changed, then those two events are dependent, not independent. Let's work through a warm-up. Try to determine whether the following events are independent or dependent and see if you can explain why. Pause the video, try these on your own, and come back for the explanations. Are the two events independent or dependent? A mosquito lands on your arm, you get a mosquito bite on your arm. While these two events are dependent, because if the mosquito lands on your arm, the probability you get a mosquito bite on your arm just went way up. So the probability of the mosquito bite on your arm increases because this first event occurs. These are not independent. In the second example, a green ball is drawn from a box with 5 balls and placed next to the box. A red ball is drawn next and placed next to the green one. So for this example, we have a box of 5 balls. I'm just assuming there are 3 green and 2 red. I don't know that for sure. I know there's at least 1 green and at least 1 red. So a green ball is drawn from the box and placed next to the box. The probability of the green ball being drawn, notice, is 3 out of 5. So probability of green is 3 out of 5 in my example. The original probability of drawing a red ball was 2 out of 5. 2 red balls out of 5 total. But now, because a green ball is gone, what's the probability of a red being drawn? it's no longer 2 out of 5. After the green one has been drawn, now there are only 4 in the box and 2 reds. So we originally went from 2/5 to now 1/2. The probability got changed because of the first event happening. These are another example of dependent events. Okay, kind of a silly one, the last one. A bird lands on your head, a bird lays an egg. Well, a bird landing on your head and a bird laying an egg, it doesn't say that the egg is on your head. It just says it lays an egg. These would be independent. There's not really any indication of a change of probability when the bird lands on your head. It doesn't really increase the probability that it'll lay an egg just because it lands on your head. So we would say these are independent events. Now, granted, these are silly exercises, but with the exception of D, which is actually a pretty good one, C and E, trying to get you to think about independent versus dependent. Think about the first event. Does it change the probability of the second event occurring? If it does change that probability, these events are dependent. If it does not change the probability, the events are independent. Let's take a look at another example. Here we're going to draw a tree diagram to solve. A coin is flipped and a die is rolled. Find the probability of getting a tail on the coin and a 3 on the die. Before we draw that tree diagram, let's talk about this. These two events, a coin is flipped and a die is rolled. So we're going to flip a coin and we're going to roll a die. Are these events dependent or independent? What do you think? Independent or dependent? These are independent. If I flip a coin, it does not change the probability for rolling the die and landing on a particular number. So I flip the coin, I put the coin down, I change to a die. Whatever landed on that coin doesn't matter to the die. We're going to roll the die and still have a 1 out of 6 probability of landing on any particular number. So we can draw a tree diagram. Remember, the tree diagram has our start node, and then we do the first event. And we're flipping the coin on the first event, which is how I know I have 2 outcomes, a head and a tail. And then when I roll the die, I have 6 different outcomes for the die. Writing the tree diagram, I can get all of my sample space, all of the events in my sample space from just reading the tree diagram. So at the start node, heads 1, heads 2, etc. And then on the tails branch, tails 1, tails 2. Now this is my sample space for the probability of experiment of flipping a coin and rolling a die. So the question, find the probability of getting a tail on the coin and a 3 on the die. So we're looking for a tail on the coin and a 3 on the die. Well, that happens right there. T3, tail and 3. There's only one of those out of a total of 12 different events in my sample space, 12 different outcomes. Now I want you to keep this in mind, and I want to point out one more thing, and I will connect them in just a moment. Notice that the probability of getting a tail when you flip a coin is 1/2, and the probability of rolling a 3 on a die is 1 out of 6. Hang on to those in the back of your head. And also remember, these are independent events. That's going to be important. And now let's finish up this part of the lesson with one more example. Rolling a single die. What is the probability of rolling a 3 if you've been told that you've already rolled an odd number? So here's the scenario. You're going to roll the die once, but you're going to close your eyes and not look at it. Someone else is going to look and tell you, you rolled an odd number. Now what's the probability you rolled a 3? Knowing that little tiny bit of information that you rolled an odd number changes your sample space in the probability. It changes the denominator and thus changes the probability. we can look at it this way. Let's write out our numbers. 1, 2, 3, 4, 5, 6. This is my sample space for rolling a single die. Okay, so that's my sample space. Original probability of rolling a 3 would be 1 out of 6. But you know you rolled an odd number. Your friend told you, hey, you rolled an odd number. And since you rolled an odd number, your focus changes, not from the whole set to now looking only at odd numbers. So now, what's the probability of 3 if you know you rolled an odd number? The number 3, there's only one of them out of a total of 3 odd numbers. So the probability has changed. These events, rolling a 3 and rolling an odd number, are dependent events. Knowing one, or one of them occurring, changes the probability of the other one occurring. Originally, the probability of 3 was 1/6, but because we know we rolled an odd number, that probability changed. It increased to 1/3. Okay. Now, so far, all that we've done with this idea of independent events and dependent events is reason it out. We've used our intuition. We've used what we know about probability and looked at the sample spaces and calculated our probabilities that way. There are formulas that we can use to determine dependent and independent events, and these are called the multiplication rules for probability. So we'll start out with the multiplication rule for independent events. And the multiplication rule for independent events says the probability of A and B occurring is equal to the probability of A times the probability of B. Notice that we have the word and we have multiplication, not addition, or uses addition. For conditional probability, this is for dependent events. So we'll make another little note here. Dependent events, we have to use a different formula. And for this formula, I'm going to write it a couple of different ways, but really it's all algebra to change things around. The probability of A and B occurring is the probability of A times the probability of B given A has occurred. This is some new notation. This little straight line up and down is given. And we would read this whole expression as the probability of B given A has occurred. We can move this formula around. Just divide both sides by the probability of A, and we get a formula for conditional probability. So this thing here, conditional probability, and we have a formula for it. Okay, so how does that relate to what we've already done? So I'm going to roll back for a second. Back up to the top with this idea of tail on the coin and 3 on the die. These were independent events, which means the probability of tails and 3, because they are independent, we can multiply the probability of tails times the probability of 3. 1/2 times 1/6. When we're multiplying fractions together, we multiply straight across on the top, 1 times 1, straight across on the bottom, 2 times 6 is 12. Hey, wait a minute. We've already seen that number before. That was what we got when we just looked at the sample spaces. Well, how do we use the conditional probability rule on something like this example in G? Well, this notion of probability of 3 if you know you rolled an odd number, this is exactly the same as probability of 3 given odd. You're given you rolled an odd number. Now what's the probability of 3? So the probability of 3 and odd over the probability of odd. In the conditional probability formula, whatever's given is what we divide by in the probability. So in this case, 3 and odd, well, the probability of 3 and odd is 1 out of 6. If we're talking about 3 and odd, 3 is odd, so those together, that's 1 out of 6. Probability of odd is 3 out of 6. Now you can do this in your calculator, or, zooming in on this one for a moment, dividing by fractions means we copy, dot, flip the second one. We're multiplying by the reciprocal. So 1/6 divided by 3/6 is equal to 1/6 times 6/3. And if we do that, the 6's will cancel out, and we're left with 1/3, which is exactly what we got, again, when we reasoned it out. In the next part of our lesson, we'll be using examples and applying these multiplication rules and conditional probability rules as we can to try to solve the problems.